Hello everyone, I'm Yuan. I will present the Dumbo-MPC, which is an efficient, fully synchronized MPC with optimal resilience. First, I will show why we need a practical synchronized MPC. In the secure multi-party computation scenario, there are some servers to gently and privately compute functions, and there are some Byzantine servers among these computing servers. Thus, the MPC must ensure correctness and privacy. To allow more convenient computation, we consider MPC as a service framework, which consists of offline and online phase. The offline phase focuses on generating Bill triples and random shares. Then, given the provided inputs, the online phase uses the Bill triples and random shares to compute the predetermined functions. Consider an application or provide smart contract. All miners gently run an MPC protocol to evaluate the smart contract while preserving the privacy. In this case, the robustness or guarantee output delivery is required, otherwise it would experience a censorship attack. Moreover, as the blockchain is globally deployed over unreliable internet, the internet may experience the transmission interruption, internet attacks, and network misconfiguration. However, most earlier MPC AAS is deployed in local area network. We consider the following network conditions. The first one is synchronized network, which has a known upper bound of network delay. The second is a synchronized network. The network delay is unknown, but the message can be eventually delivered, which has made minimal assumptions about the network condition. The most known TCP network is asynchronized. And most MPC EAS works rely on the synchronized network. Take the BGW as example. We have to gather all honest parties' shares to correct malicious shares, which is possible in the synchronized, because we cannot wait all honest parties' shares. Many synchronized robust MPC try to inject unresponsive parties, but in synchronized, honest parties can be eventually all injected, and thus compromising privacy. Therefore, we aim to construct an MPC protocol in the fully synchronized and optimal resilience network, which is concurrently efficient and provides and robustness. We first show some recent work on a synchronized MPC. In GRR98 and GS23, all party first generates random shares using a verifiable secret share and passing commitment. They also need the synchronized Byzantine agreement to allow honest parties to agree on the shares and commitment they have received. Finally, they add the shares in the agreed set and also compute the commitment. Then, given two random shares of T degree A and B, all parties perform degree reduction. Concretely, each party multiply A and B to obtain 2T degree shares AB, and use a verifiable secret share to share these 2T degree shares. More importantly, each party must prove the correctness of random shares A and B is respectively bind to commitment C sub A and C sub B. And the RT degree shares AB is indeed the product of T degree shares A and B. Finally, each party will check all proofs and conduct RT degree interpolation to obtain the T degree shares of AB. However, this work remains the following efficiency issues. First, it has various case cubic communication complexity pure triple. Second, each party needs to share 3 secrets to obtain 1 triple. In the HoneyBadgerMPC, there are a robust online phase and a non-robust offline phase, which requires all parties to be honest. The offline cannot preserve guarantee output delivery, but can generate triples much faster than GS23 in the good case. But non-robust offline eventually leads to the non-robust online phase. In GS23, all phase is robust, but it is very inefficient. In HoneyBadgerMPC, although the offline phase is not robust, but it is efficient in the good case. Now, can we have the best of both? Here we present our solution, Dumbo-MPC. From a high-level overview, Dumbo-MPC consists of fast pass and pessimistic pass. The fast pass has linear overhead and concretely more efficient than HoneyBadgerMPC. It will abort if timeout or detect misbehaviors. Then, all parties exclude an asynchronous fallback protocol to agree on the fast pass progress. Finally, all parties enter into the pessimistic pass, which is an asynchronous triple generation protocols from compact KZG polynomial commitment. The pessimistic pass has quadratic overhead and more efficient than GS23. As Python commitment allows to interpolate in the exponent to derive any evaluations commitment, and it is more convenient. Hence, we introduce a hidden evaluation interface to KZG commitment to enable proving correct multiplication by zero-knowledge proof of knowledge of product relations over Python. The hidden evaluations satisfy binding and hiding properties. We also using KZG commitment to initiate the SOTA batch AVSS called hbACSS. We found that the hbACSS lacks concurrent composability. We use INDCCA secure public encryption and leverage different keys in different dealers' instances to patch the vulnerability. Based on the hbACSS and the augmented KZG, we construct a more efficient triple generation protocol. The protocol can extract random shares by super-invertible matrix and reduce the secrets to be shared from 3 times n to n plus 6. Now, we give our dual mode triple generation framework. First, all party excludes fast pass to continuously generate triples. When the fast pass failed in round R, all honest party must have finished the round R sub R-2. Then, the fallback mechanism is a conceptually minimum budgeting agreement, which takes one or two consecutive values as input and agree on the round that all honest party has generated correct triples in the fast pass. Finally, all honest party enter into pessimistic pass to robustly generate triples. For the evaluations, our Dumbo-MPC is faster than GS in the bad case, as shown in the left figure. In the good case, Dumbo-MPC is faster than HoneyBadgerMPC plus the time for secure fallback. In face of dynamic crash for 4 nodes, Dumbo-MPC can robustly generate triples and is efficiently than HoneyBadgerMPC and GS23. We also evaluate the latency of preprocessing triples for victory auctions and mixing net. As shown in the figure, Dumbo-MPC is concretely efficient. In a summary, we help both an asynchronous MPC AES framework called Dumbo-MPC, which can efficiently and robustly generate triples in the pessimistic path, and also can harvest the progress in the fast path. The fast path is slightly faster than HoneyBadgerMPC and can secure change to pessimistic path via a synchronized fallback mechanism. Thanks.